Hello everyone. In this lecture, we're going to solve some of the exercises in chapter 13, assessment. So that will be page 468 and 469. We're going to solve some selected questions about gases. We're going to be applying different gas laws like ideal gas law and combined gas law and other gas laws. I have limited access to resources, so I want to apologize if the handwriting was not so clear in certain questions. Now, before we start, let's review the basic formulas that we are going to be using. So let's start, let's say, with the combined gas law. So I have P1 V1 over T1 equals P2 V2 over T2. Now, when do I use the combined gas law? It's when I have a certain gas at a certain set of conditions and I am changing these conditions. So when you read the question, you're going to have two volumes or two pressures or two different temperatures. So you would know that you want to use the combined gas law or one of its derivatives. Now, actually, you can memorize only the combined gas law and then you can figure out any other law using it. So let's say, for example, you memorize the combined gas law and the question was at a constant temperature. So if the temperature was constant, it means T1 and T2 are the same. You can cross them out and you'll be left with P1 V1 equals P2 V2, which is Boyle's law, right? Now, let's say that the question was at a constant pressure. So if the question was at a constant pressure, then the pressure is constant. P1 and P2 are the same, so you'll be left with V1 over T1 equals V2 over T2, right? Now let's say that the question was at a constant volume, so now the volume is constant. So since the volume is constant, I will cross it out and I will have P1 over T1 equals P2 over T2, which is Lusak's law. So you can always start by writing the combined gas law, and then you can decide, okay, which condition is constant, and you're going to end up with one of these formulas that you can use to solve the question. Now, the other formula that you have is the ideal gas law. Now, the ideal gas law, you have a gas at a certain condition and you have one piece of information is missing. So you have the pressure, you have the volume, you have the temperature, and maybe the moles is not given. Or maybe you have the moles, you have the pressure, you have the temperature, but the volume is missing. So the ideal gas law is PV equals nRT. Okay, so P is the pressure, and the pressure could be in atmosphere or kilopascal, depending on the question. V is the volume. The volume should always be in liter. So if it was in milliliter, you have to divide by 1,000. N is the number of moles. And T is the temperature in Kelvin. Actually, in all the gas laws questions, you should have the temperature in Kelvin. So the first thing that you have to do to check if the temperature was not in Kelvin, make sure to convert it into Kelvin. Now, how about the R? The R here is a constant. And you have different values of R that depends on what unit of pressure are you using. So if the pressure was in atmosphere, the R will be 0.0821. That's if the pressure was in atmosphere. More atmosphere liter per mole Kelvin. If the pressure in the question was given in kilopascal, then you will use R as 8.314 kilopascal liter per mole Kelvin. Now you have a table in the book of different units of R and it was explained in lecture 13.2. So if the question, you have the pressure is in atmosphere, then you can use R as 0.082. If the pressure was in kilopascal, then you have two options. Either you convert the R into 8.314. So if the pressure is given in kilopascal, the R is 8.314, or you can convert the pressure into atmosphere and then you use 0.082. But of course, memorizing the values of R at different units would be easier than converting. Now let's start solving questions, starting with number 58. So a sample of air occupies 2.5 liters. So this is the volume at a temperature of 22 degrees Celsius. So this is the temperature. What volume will the sample occupy? So this is another volume, right? So this is V1, 22.5, and this is T1, 22. And they said, what volume would the gas occupy? So they want V2. If the temperature was 43 degrees Celsius, so this is T2. Okay, now assume that the pressure remains constant. So at a constant pressure, you have a gas at different volume and different temperature, yet the pressure is constant. So that would be Charles' law, right? So you'll be using V1 over T1 equals V2 over T2. Now let's go back to the question. See that the temperature here is given in Celsius, right? Remember that you have to convert it into Kelvin. So in the question, V1 is 2.5 liters. T1 is 22 degrees Celsius. You have to convert it to Kelvin, so you add 273, and T1 is going to be 295 Kelvin. Then you have V2 is the required. They are asking you to find V2, and T2 is 43. Again, you have to convert it to Kelvin, so you add 273, and that would be 316. Now you are going to substitute in this law. So V1 is 2.5 over 295 equals V2, which is the unknown. This is the unknown X or V, and T2 is a 316. Now you find X the same way you do in mathematics. You solve this equation for X. So if you want to solve it, you can multiply by the reciprocal. So you will multiply here by 316 over 1. So to find X, X is going to be 2.5 over 295 times 316 over 1. And X, which is the volume, is going to be 2.68. I rounded the answer, and this is the volume in liters. Since V1 is in liter, V2 also is going to be in liter. So this is a question using Charles' law. Let's move to another question. Number 59. What is the pressure? So they wanted to find the pressure of a fixed volume. So this is a key word here. The volume is fixed. So they wanted to find the pressure. They wanted to find P1 of hydrogen gas at 30 degrees Celsius. So this is T1, right? And you have to convert it into Kelvin. So you are going to add 273. So this will be 203 Kelvin. If it has a pressure of 1.11, so this is P2 at 15 degrees Celsius. So this would be T2, and again you have to convert it to Kelvin. So you add 273. So clearly this is the relation between the pressure and temperature at a fixed volume. Now let's say you did not figure out at the beginning which law to use here, but you know that you have two pressures, you have two temperatures, so you start P1 V1 over T1 equals P2 V2 over T2, and then since they said that the volume is fixed, so you cross off the volume, and you are left with P1 over T1 equals P2 over T2, and you are going to apply Lusak's law. Or you can figure it out from the beginning that it's only pressure and temperature relation, so it's P1 over T1 equals P2 over T2. And now to solve the exercise, you are just going to substitute the values in this formula. So P1 is the unknown, this is your X or your P, and then T1 is 303 equals P2 1.11 over T2. Okay, now since the pressure here is in atmosphere, then the final answer also is going to be in atmosphere. You solve this equation and P is going to be 1.17 atmosphere. Now let's move to the second exercise. Number 60. A sample of nitrogen gas is transferred into a large flask as shown in figure 13.14. Now figure 13.14 is in your book, page 468. You already have the pages for the chapter assessment, but I will write the conditions that are mentioned in the figure. So according to figure 13.4, V1 is 500 milliliter, P1 is 108 kilopascal, T1 is 10 degrees Celsius. As for V2, it's 750 milliliter, and T2 is 21 degrees Celsius. These are given in the question. Now, what is the pressure in the second flask? So they wanted to find P2. Now, which gas law do you think we have to use here? You have two volumes, two temperatures, and two pressures mentioned in the question, right? So definitely you're going to use the combined gas law. P1, V1 over T1 equals P2, V2 over T2, right? Now I wanted to always keep an eye on the units. In the combined gas law, the temperature should be in Kelvin in any gas law, and the volume could be in liter or in milliliter as long as the units are homogeneous. So when you check this equation, V1 is in milliliter and V2 is also in milliliter, so you don't need to convert. You can just use the volume in milliliter. P1 is given in kilopascal, which means that P2 will also be calculated in kilopascal. Now the temperature should be definitely in Kelvin. So T1, if I'm going to convert that to Kelvin, it will be 283 Kelvin, and T2 is going to be 294 Kelvin. Now I will substitute these values in the combined gas law. So P1 is 108, P1 is 500, T1 is 283, equals V2 is 750. P2 is what I want to calculate. I don't know it, it's my unknown, and T2 is 290. Now I'm going to solve for P. I will do the algebraic steps here. So I will erase this one here for more space. And then we are going to solve this equation. Now, of course, you need to use your math skills to find for the unknown. So I'm going to solve these. So you plug in these numbers in your calculator. So I'm going to end up with 190.8 equals, and then I'm going to do these in the calculator, 750 over 294. So I will have 2.55 P. Now to find the pressure, I'm solving for the unknown, which is the P. So I'm going to divide both sides by 2.55, right? And then the pressure is going to be 74.82. And of course, it's going to be in kilopascal since the unit of pressure given in the question was in kilopascal. Let's move to another question. Number 65. So list two conditions under which the gas is least likely to behave like an ideal gas. Now, what makes a gas an ideal gas? In ideal gas, we are assuming that the particles are so far away from each other that we neglect any intermolecular forces between them. We neglect any attraction or repulsion among these forces because they are far away from each other. That's for the ideal gas. Now, what happens if you applied a high pressure on this gas? Now, these particles are going to come closer to each other. And when the particles are closer, now the intermolecular forces are going to be significant. I will not be able to ignore them. So, under high pressure, as the particles come closer to each other, the intermolecular forces are going to be significant. And that's, for example, if you take a gas cylinder, under high pressure, you can actually liquefy a gas, right? If you're going to apply a high pressure on the gas, like the one you have in a gas cylinder, the gas is going to be liquefied because under high pressure, the intermolecular forces or the attraction among the particles is going to increase. So since I have an attraction here, it is less ideal or more real. And the same goes for temperature. Under high temperature, the particles are far away from each other. When you decrease the temperature, these particles, now they have less energy, so the particles under a lower temperature are going to start coming closer to each other under low temperature. And as they come closer to each other, the intermolecular forces between them is going to be significant. I will have more attraction among these forces, and since I should consider the intermolecular forces, it means that the gas is more real and less ideal. So if I want to set the conditions at which the gas is the least ideal, that would be under high pressure and low temperature. Under high pressure and low temperature, the gas is a real gas. Number 69. Calculate the number of moles of O2 gas. So here they wanted to find the number of moles held in a sealed container of 2L. L is liters, right? So this is the volume at 3.5 atmosphere. This is the unit of pressure. So this is the pressure, and 25 degrees Celsius. So this is the temperature. Now, of course, if the temperature is in Celsius, you have to convert it into Kelvin. So this one is going to be 298 Kelvin. Now, check this question out. Here you have one volume, one pressure, one temperature. So you don't have P1 and P2, V1 and V2, right? And also they wanted to find the number of moles. So which gas are you going to be using here? Gas law. Sorry, it's the ideal gas law, PV equals nRT. You don't have P1 and V1 and T1 and T2. You only have one value of volume, one value of pressure, and one value of temperature, and they wanted to find the number of moles. So you'll be using the ideal gas law, PV equals nRT. So the pressure here is 3.5 atmosphere. The volume is 2 liters. It's already given in liters, so I don't need to convert. The number of moles is required. The temperature is 298 Kelvin. Now, R, since the pressure is given in atmosphere, then I will use R as 0.0821 because the pressure is given in atmosphere. Now, all what you have to do is to plug in these values. So I have the pressure is 3.5 times 2 equals N is the unknown, 0.0821, and times 298. So I have it times 298. I don't have space here. Now I want to find N, right? So I'm going to solve 3.5 times 2 is 7. So here I would have 7 equals 0.082 times 298 is 24.46 N. And then I will solve for N. I will divide both sides by 24.46, and N is going to be 0.286 moles. Let's move to number 72. Determine the density of chlorine. Now this equation is easy because you already have a formula to calculate the density. The formula was explained in lecture 13.2, and you have the formula in the book. The formula for the density of a gas is that D equals M, where M is capital M, the molar mass, times the pressure, over R times T. So you memorize this formula and you use it when you want to find the density of a gas. Now what do I have here is chlorine gas. Chlorine gas is Cl2, and I want its molar mass because this M here is the molar mass. So the Cl, you go to the periodic table, Cl is 35.5 times 2, and you're going to have 71 gram per mole. Now you substitute these values in the formula. D equals the molar mass, which is 71, the pressure, which is given in the question as 1 atmosphere, R, again, since the pressure here is an atmosphere, R is going to be 0.0821, and T, which is the temperature in Kelvin. So here you have it given in Celsius. You have to convert it. So you add 273. So the temperature here is 22 plus 273. And then you just need to plug in these values in the calculator, and the density is 2.93 gram per liter. This would be the unit of density. Now let's move to number 77. How many moles of helium gas, so they wanted to find the number of moles here, would be required to fill 22 liters. So this is the volume at a temperature of 35 degrees Celsius. So this is the temperature in Celsius. Again, you have to convert it into Kelvin. So that would be 308. You add 273. And a pressure of 3.1 atmosphere. So this is the pressure. So you have a volume, pressure, temperature, and you want to find the moles. Which formula are you going to use? The ideal gas law. PV equals nRT. And again, you just have to substitute the values. The pressure is 3.1. The volume is 22. In this formula, the volume should be in liter, okay? The mole is the unknown. Again, since the pressure is in atmosphere, the R will be 0.0821. And the temperature in Kelvin is 308. And then you will solve for N, and N will be 2.69 moles. Now, let's assume that in the question they asked you to find the mass, not the mole. They said, find the mass of helium. How do you solve this kind of a question? Well, you're going to do the same. First of all, you're going to find the moles of the gas, which is going to be 2.69. So also you're going to apply PV equals nRT to find the moles. And after finding the moles, you can find the mass. Remember that mass equal mole times molar mass, right? So if the question was find the mass of helium instead of finding the moles of helium, you still have to calculate the moles first. And after finding the moles, you're going to apply this formula, mass equal mole times molar mass. So it would be 2.69 times the molar mass of helium, which is 4, and then you will find the answer in grams. Now that's all for here. You're gonna have to solve other exercises, so you can do these exercises for a practice. You can do number 53, 56, 63, 67, 75. You can solve these exercises as a practice. These exercises are in the chapter assessment. That would be pages 468 and 469. The answer key for these exercises will be posted. Study well. Good luck. If you have any questions, please don't hesitate to contact your teacher for more clarification. Stay safe and God bless you.